All right, just a couple of notes on my end. Uh, the exams. I'm going through them right now. I've graded the multiple choice section. I'll have the matching and the short answer probably done this afternoon. So I'm hoping I'll have everything done by the end of today, tomorrow at the latest to get the rest of those in. Thus far, multiple choice section went pretty well. Average grade was right around 75% on the multiple choice section. Some did considerably better. Lowest grade was 50%, and that's usually encouraging as well. That means usually you do that, you can make your way through the short answer and the other part as well. As far as current assignments go, there were a number of post lectures that were due. The Chapter 3 homework is due tomorrow night in Connect. The Chapter 3 quiz is due Sunday night in Connect. So you got both of those assignments out there. We're going to spend probably the first 5 or 10 minutes of today just doing a couple more nomenclature examples, try to get you a little bit more familiar, a little bit more comfortable with those. And then hopefully between the remaining homework and the quiz and the lab, you should feel confident enough that you can give that nomenclature proficiency a try. Even though it's not due for quite a while, it's not due for about another month almost. With as much time as we've spent in the past week, 2 weeks on this material, it's good to kind of go at it when it's the most fresh. And again, there's no penalty for not getting it and not passing it on the first try. So, if you're feeling pretty good after the homeworks, be a good time to go after that and try it. So those are the immediate announcements. Any questions? All right. So let's do a little bit more practice, and then we'll get into Chapter 4 and we'll start talking about some chemical compounds and some bonding and things. So when we're practicing, when we're trying to name compounds or write out chemical formulas for compounds based on name, there are some things that we can do that will definitely help. One of those things is identification. Can we identify what it is that we are supposed to be doing? Can we identify the type of substance that is present? And if we can do that, then we're well on the way to at least having a chance of naming it correctly. So when I see a name like nitrogen pentoxide, a couple of things ought to come to my mind immediately. Nitrogen and oxygen are both nonmetals. And I've got a prefix in there. So this is a covalent compound. As a covalent compound, I know it's going to fall into that prefixing naming system. Nitrogen is N. The fact that there is no prefix here indicates that there is just one nitrogen. Oxide means I've got oxygen. The prefix pent means 5. So my chemical formula here is NO5. I can use similar kinds of logic for 3 other compounds on this page. Tetraphosphorus hexafluoride, oxygen difluoride, boron triiodide. All 3 of those have the same kinds of issues. 2 nonmetals bonded together. I've got a bunch of prefixes in there. So it's just a matter of recognizing what elements are there and then attaching the appropriate prefixes in the right place. So for tetraphosphorus hexasulfide, I'm dealing with phosphorus. Phosphorus is P. Prefix tetra refers to how many. Four. Sulfide, so I'm dealing with sulfur. Prefix hexa refers to 6. So the compound here is P4S6. In oxygen difluoride, I have oxygen, so that's O. How many oxygens are there? If it has no prefix, it's
1.
Just 1. Thank you. Fluoride is F, fluorine. Prefix di refers to 2. So compound here is OF2 oxygen difluoride. In the last one, we've got boron, that's B. Again, no prefix on it, so we're talking about 1 boron here. Iodide would be iodine, I. And the prefix tri, meaning 3, Bi3 is the name of this compound, or the formula for this compound, boron triiodide. So if I can recognize that it's covalent, going in this direction is actually not all that difficult. I just need to recognize what 2 elements are there and then turn those prefixes into the subscripts for those elements. So what if I don't have a covalent compound? Well, in all of these other cases, I should be able to recognize that I've got metals here. Cesium, calcium, iron, zinc. And if those are the cases, I'm dealing with ionic compounds in each of those spots. Remember, if I was dealing with an acid, the acid is the other kind, the third kind of substance here. If I was dealing with an acid, every single acid ends with acid as its compound name. And if that was the case, then I know I was starting with hydrogen and I've got some other something attached to the hydrogen. So how do I handle these? Well, since I know they're ionic compounds, I know that they're composed of ions. The question is, what are the ions? And in some cases, it's a matter of recognition. I have to know what my polyatomic ions are. And in some cases, it's a matter of recognizing charge and position on the periodic table. So in the case of cesium bicarbonate, I know I have cesium, Cs. What is going to be the charge on that cesium?
Is it 2?
Did you say 2, Skylar?
Yeah.
Okay, it's not 2. It's 1. Now, how did we know it was 1?
It's in the first group on the periodic table.
Exactly, Savannah. And you're going that direction as well. If we have something that does not have a Roman numeral, then our immediate thought needs to be going to the periodic table and finding its position on the periodic table. Because in those cases where we don't have Roman numerals, that means it only has one charge, and that charge is going to be directed by its position on the periodic table. Remember, the first column all make +1 charges. The second column all make +2 charges. The group 13 all make +3 charges. So cesium is going to be a +1 charge. Now, the bicarbonate ion, this is one that you need to know. It's HCO3 with a -1 charge. So here I have a case where my positive ion and my negative ion both have the same charge in terms of its magnitude, a +1 and a -1. And when that is the case, they exist in the molecule as a 1-to-1 ratio, CsHCO3. So the formula for cesium bicarbonate, sometimes known as cesium hydrogen carbonate, is CsHCO3. All right, let's look at calcium sulfite. Again, calcium here has no Roman numeral on it, so we should be able to figure out its charge based on position on the periodic table. I'm sorry? +2. The sulfite ion, again, one that you're just going to have to pick up over time if you haven't learned it already, SO3 -2. Once again, my charges match, so I don't need to crisscross. I just put the two together, CaSO3. If my charges did not match, that's when I would have to cross them up to find the subscripts. But since they match, I don't have to do that. Iron 3 phosphide. Okay, now we have a Roman numeral. What does that Roman numeral dictate? Does it dictate the charge or the subscript? Okay, I've heard subscript mumbled under breath here in the classroom. It's been mumbled in the chat. It's incorrect. Roman numeral indicates charge. The reason we set Roman numerals is when we have elements that are capable of having more than one type of charge. And when we don't have Roman numerals, that indicates that we don't have more than one charge. So the iron 3 here means that we have the iron 3+ ion. Now the other key note here, phosphide. The fact that this ends in IDE should tell you something. What should it tell you? It should tell you that there's only one element in this ion. It's phosphorus. So IDE is kind of the equivalent of what we saw in the non-Roman numeral metals. I should be able to derive its charge from the periodic table. And so to that end, phosphorus is in group 15. What should its charge be? -3. Remember, for the nonmetals, you count kind of backwards. You count out from the noble gases. So group 17 is a -1, group 16 is a -2, group 15 is a -3. And so I've got matching charges here again, +3 and -3. I don't need to crisscross. FEP is the correct formula. All right, there's one more example here, and I've saved it for last for a particular reason. Because of the ones here, it's kind of the most tricky. Not because it's really hard, just because it's different. All right, zinc has no Roman numeral, which means it doesn't have multiple charges. It only has one charge. What is the charge on zinc? All right, Savannah says it's +2 in the chat. And she is correct. It is +2. If you recall, we talked about that small triangle pyramid in that little subsection of the transition metals, where zinc is +2, silver is +1, cadmium's +2, indium's +3. Those ones do not change. And they just kind of cascade down like that. Nitrate ion is one of your polyatomics. You got to know it. NO3, -1. So here we have a scenario where the charges do not match. And when the charges do not match, that's when we have to crisscross the charges to get the correct subscripts. So the 1 for the nitrate becomes the subscript for the zinc. The 2 from the zinc becomes the subscript for the nitrate. How do I express that there are 2 nitrates? I can't just simply put ZnNO3 2, because that's going to look like I have 32 oxygens. How I need to do it, I have to put parentheses around that NO3 to tell me that there are 2 of those NO3 ions. And so there you have it. A little bit of extra practice just to kind of get us warmed up and put into the right mode of thinking. Any questions about any of these 8 examples? All right, let's do just a couple on our own here. Just to kind of see how we're doing. All right, so we'll do these 2 that are in the multiple choice here. Mg3N2. First thing you have to do, identify it. Once you identify it, you should be able to name it a little bit easier. So, is this ionic, covalent, or acid? David has chimed in. He thinks it's covalent. All right. Savannah has said it's covalent. What about you four here in the room? All right. Okay. David has changed to ionic. We got another one saying covalent. Walk me through it. Alana, take me through it. Okay, if you couldn't hear, she said she thinks it's ionic because magnesium is an alkaline earth metal. Yeah, it really is that simple. If you have a metal and a non-metal, it's going to be ionic. So don't be fooled by all the subscripts. The subscripts just help us to either balance charge or show the bonding. If I've got a metal and a non-metal, it's going to be ionic. Now, the fact that it's an alkaline earth metal, do alkaline earth metals change their charge? No. So right away, we can pretty much eliminate all of the options other than the correct answer, because this prefixing system is only used by covalent compounds. We've already determined that this is ionic. And those refer to charges if there are multiple charges possible. Since alkaline earth metals don't change their charge, we don't need to specify a charge. Magnesium nitride is the correct answer. It's B. All right, let's do one more example for the good of the order. CCl4. Identify it first. What's in it? What kind of compound is it? Okay, Adria, it's covalent. What leads you to that conclusion? We've got two nonmetals. We've got carbon, which is a nonmetal. We've got chlorine, which is a nonmetal. So what's the name of the compound then? We've got a couple of guesses coming in on D. Do any of the other answers make sense? Okay, so yeah, by identifying it as a non-metallic, a covalent compound, Roman numerals go out right away. Carbon chloride, we have to know that there are prefixes involved, and neither of those elements has a prefix, which would mean that this is an ionic name, so that's out as well. It's the difference between C and D. And remember, mono is assumed on the first element unless it's got multiple atoms. So we don't need to write mono on the first carbon, it's D. All right, so your homework and quiz out of chapter 3 are all sorts of problems along this line. And again, being able to peel it off and look at it and say, okay, what do I have here? Is this ionic? Is this covalent? Is this an acid? goes a long way to you being able to classify it and name it correctly, because you'll be able to recognize, okay, I've got a covalent compound here. This is what I need to do. Okay, I've got an acid here. Let's figure out what kind of acid it is. Let's name it from there. And so that's where we're going to leave chapter 3 for now. We're going to move into chapter 4. Maybe. And chapter 4 for us is going to fall into a couple of topics. We're talking about chemical composition. We're going to get into some calculations here in chapter 4 after kind of leaving behind calculations for a couple of weeks there in chapter 3 and parts of chapter 2. So in chapter 4 here, we're going to talk about 3 main ideas, and they're all interrelated with each other. We're going to talk about percent composition, which is just a way of using mass of a substance to give us some idea of the chemical makeup of a compound. We're going to talk about something called moles, where we get into discussions of being able to bridge a gap between mass and number of particles of something. And then we're going to use both of those together to actually do some elemental analysis and be able to answer a question of, if I have a substance, I know roughly what it's made out of. Can I calculate and figure out its formula? Can I figure out what its chemical formula is? And then at the very end, we'll get into talking a little bit about solutions and how solutions are put together. Now, as far as percent composition is concerned, percent composition, again, is a look at the percent by mass of the different elements that make up a compound relative to the total mass of the compound. So an easy way of thinking about this is, if I'm looking at this compound here, hematite, iron 3 oxide, the percent by mass of iron would be equal to the mass of the iron divided by the mass total multiplied by 100%. I could do something similar with oxygen. The mass of oxygen, mass percent of oxygen, would be equal to the mass of oxygen over the total mass multiplied by 100%. Now, common uses for mass percent are for doing things like this. If I have a mineral sample, can I figure out what iron compound is in that mineral sample? I can do so by evaluating how much iron is in that sample compared to how much oxygen. If the percentage of iron is higher, I know it's the iron 2 oxide, the woostite. If the percentage of oxygen is greater than expected, then I can conclude that it's the hematite, the iron 3 oxide. But I can use those values to give me an idea of just how much iron is in the sample and how much I need to take into consideration. So that's one application for percent by mass. In general, we can determine the mass percent for any element in any compound by dividing the mass of the element that we're interested in by the mass of the sample and multiplying that by 100%. And so this can be done experimentally, where I have data. Let's say that I am doing a chemical reaction in the lab and I'm taking copper and reacting copper with sulfur. And I put those two elements into a reaction vessel. I let the reaction go, and I can see, okay, the copper weighed this much beforehand, the product weighs this much after, and I can figure out how much copper percentage-wise is in the compound based upon my law of conservation of mass and some other calculations that I can do. This can also be done with a chemical formula. So let's take that example from the previous slide. If I have iron 2 oxide, FeO, the percent of iron would be equal to the mass of iron divided by the mass of FeO times 100%. And these masses I can get from my periodic table. The mass of iron is 55.85 AMU. The mass of iron oxide would be 55.85 plus 16 for oxygen AMUs. And so using the periodic table, I could find the percent composition of a compound just by comparing the values on the periodic table to each other. And I'd get a percentage that way. So there is a lot of utility in percent composition if we know how to use it. Now what we're going to get into obviously here is how to go about doing those calculations. And so again, we can get it in a number of different ways in different sources. Here's an example of an experimental example. If I know the total mass of my sample and I know the compositional masses of my three elements that make up that sample, then finding the mass percent of any of them is just a matter of comparison. All I need to do is take the mass of that element, whether it is sulfur or iron or copper, and compare it to the mass of the total sample in the denominator. And I could compare any of them individually. So let's actually just do that as an example here. So I've got 3.67 grams of sample, and it's divided among 1.28 grams of sulfur, 1.27 grams of copper, and 1.12 grams of iron. To find the percent sulfur, I would take the mass of the sulfur, 1.28 grams, divide by the total mass, 3.67 grams, multiplied by 100%. And if I do that calculation, 1.28 divided by 3.67 times 100%, 3 significant figures because I have 3 in the numerator and in the denominator, I get 34.9% sulfur. I can do a similar calculation for percent copper. 1.27 grams of copper divided by 3.67 grams total times 100%. 1.27 divided by 3.67 times 100 to 3 significant figures again, 34.6% copper. And then lastly, my percent iron, same calculation, 1.12 grams of iron divided by 3.67 grams in total times 100%. Notice that my units here, grams, cancel out. I just have percentage and the element left over. 1.12 divided by 3.67. I get 30.5% iron. Now notice that if I add these 3 percentages together, I would get my 100% total out of it. Now that's an important thing here because what this means is that if I have a sample like this, I don't actually have to do all 3 calculations like this. I could have found the percentage of iron simply by taking 100% and subtracting the 34.9% sulfur and the 34.6% copper. And if I had done that, 100 minus 34.9 minus 34.6, I would have got the same 30.5% iron. So something to keep in mind if you're doing percent composition problems like this, the components always have to add up to 100%. So if I have 2 components and I figured out the mass percent of the first, everything that's left over out of 100% has to be the other component. I can just subtract it from 100. I don't need to do the division again. If I have 3 components, I can figure out 2 and subtract to find the third. If I have 4 components, I can figure out the first 3 and subtract to find the fourth. And it doesn't seem like it's all that much, but those little things can kind of add up in terms of being able to do things more quickly, more efficiently, and with fewer mistakes. Yes. Yes. I've got grams in the numerator and in the denominator in each one of those. So the grams will always cancel out. You'll end up getting a percent value as a result each time. Alana? So there will be cases where you'll be given 2 percentages and the third one will be implied because of that. So especially when we do like empirical formulas, which is toward the end of this chapter, that's pretty common, where you're told you've got a compound that's made out of carbon, hydrogen, and oxygen. It's 30% carbon, it's 5% hydrogen. What is its empirical formula? And the implied part of that is, well, if it's 30% carbon and 5% hydrogen, that means that 35% of it is those 2 elements. The remaining 65% must be the oxygen. So it's implied in there. It's not stated directly, but you should be able to, based on your knowledge of percent compositions, be able to figure out the missing piece of the puzzle. So yes, this information does come in handy in those other kinds of circumstances as well. All right, so we already did that. And like I said previously, we know that the 3 components have to add up to 100%. Now the question is this: if I had a different sample of the mineral, would the mass percentage change? And hopefully you can kind of pick up the inference here. The answer is no. Why wouldn't it change? The chemical composition hasn't changed. And why won't it change? Well, it's pretty simple. We're talking about a mineral called chalcopyrite. Chalcopyrite. Chalcopyrite has a particular chemical formula associated with it. Has a certain combination of iron and copper and sulfur. If I mess around with the mass percentages, I'm going to end up changing the chemical formula of that substance along with it. So our law of constant composition, which we talked about way back in chapter 1, applies here directly. Constant composition has a direct reference to mass percent composition in compounds. If I change the mass percent composition, I'm going to end up changing the chemical formula as a result. And so if I look at a chemical formula, if I look at any given sample of a chemical compound, what I will find is that the mass percentage of one element to another is unchanged in that compound, regardless of whether I have the tiniest speck of it or the largest truckload of it I can find. The chemical composition is unchanged by amount and unchanged by percent composition. Second question here, if I had 100 grams of this sample, how much copper would I have? Well, you have to take into consideration your definition. Percent equals parts per 100. That's the literal definition of percent, per 100. So if I have a 100-gram sample, based upon this definition of percentage, 34.6 grams of that sample would have to be copper. And that particular relationship will become much more relevant as we go. So we'll stop there for today. On Friday, we're going to get into section 2 out of chapter 4, and that is talking about moles and mole quantities. And in particular, what we're going to start to do is build a relationship between mass and particles for a given compound. Because up until this point, all we've talked about really is mass. And the thing about masses is different elements contain different masses. So if I have 50 grams of each sample, in some compounds, some elements, that's not very much. Whereas in others, it's quite a bit. So how do we standardize our descriptions of mass to be able to compare amount of one thing to another much more directly? That's what we're going to talk about on Friday. Have a good afternoon.